For the next example, we have this figure that shows a balanced Y-to-delta three-phase circuit. So the phase voltages of the Y-connected source are VA equivalent to 110 angle 0, VB is 110 angle negative 120, and VC is 110 negative 120. So based on that given phase voltages, we can say that this is a positive sequence source. So the difference between the previous example is that there are now line impedances. We have right here ZL is given to be 10 plus J5 ohms. Then lastly, we have the impedances of the delta connected load, which is equivalent to 75 plus J225 ohms. So now determine the phase currents in the delta connected load. We need to determine IAB, IBC, and ICA. So now that we have ZL right here, if we perform KCL right here, for example, KCL right here, like what we did in the first method on the previous example, we will now have multiple unknowns. So IBB is still unknown, IBC is still unknown, and then ICC is still unknown. So the best way for this example is to use the per phase analysis. So meaning we need to transform the circuit into Y to Y. We have V, A, N. Let's write our other given values right here. VBN 210 angle negative 120 and VCN 110 angle 20 degrees. And then we have ZL equivalent to 10 plus J5 ohms and Z delta equivalent to 25 plus J225 ohms. For this example, we will need to use the per phase analysis. So I need to convert the circuit into Y to Y balanced system. So per phase analysis. So remember that the values in the per phase analysis from the name itself are the phase values. So phase voltages, phase impedances of the load, and then the phase current. And remember that the phase current and the line current of a Y to Y balance source is just equivalent. We have negative AN, then we have right here our ZL, Z line, and we have right here our Z delta over 3. We have EAN. Right here we have our IAA. So getting the value of IAA, we use KVL right here. IAA is equivalent to VAN over GL plus G delta over 3. So this is equivalent to 1.26, the angle of negative 66.37 amperes. So having the value of IAA, we can now solve for, we can now get the values of line currents IBB and ICC. So we have 1.26 and negative 186.37, and we have 1.26 equivalent to positive 53.33 years. Now we have our line currents. Using these values of the line currents, we can now solve for the phase currents. Phase current is equivalent to line current over square root of 3, then you add the angle by 30. We have IAB equivalent to IAA over square root of 3, and you add the angle by 30. So this is equivalent to 0.727 angle of negative 36.37 degrees. Now if we have the value of IAB, we can now get the value of IBC and ICA equivalent to 0.727 angle of negative 156.37 years, and ICA is just equivalent to 0.727 angle of 83.63 degrees. We have now these values. Or another way to get the phase currents, so we can use the phase voltage VAN right here. So this is the figure of this. So this is the figure. This is V, this is A and N. So we have the voltage right here, VAN. So the voltage VAN just equivalent to G delta over 3 times IAA. We have 99.61 angle of 5.20 degrees volts. Now if we have the value of the phase voltage at the load side VAN, we can convert this, or we can relate this to the voltage, to the line voltage VAB. So VAB is equivalent to square root of 3 times the phase voltage VAN, and you add the angle by 30. So this is equivalent to 171.82 angle of 35.20 volts. So where is this VAB located? Looking at the figure, VAB just right here between two nodes. So right here is VAB. So if we have VAB, IAB, that's equivalent to VAB over D delta. So going back, IAB is just equivalent to 0.727 angle of negative 36.37. So which is the same with this value right here.